Hi Tyler, this is Lydia. Hope you're doing well. As promised, I'm putting together a corrections video for your ACT Test 59F. We're going to start off with the questions in the elementary algebra section first, and then we will move to the intermediate algebra, and it has some geometry in there too. So let's start with question number 7. It says, what is the least common denominator for adding the fractions 4/15, 1/12, and 3/8? So what that's asking is, if we were to set this up as an arithmetic problem, so we have these three fractions that we're adding together, we of course need to have some sort of denominator that relates 15, 12, and 8, because we can't just add them together in this form. So to do that, we need to consider the factors for each of these denominators. And in particular, we're going to go all the way to the prime level of those factors. For example, if we were to look at the number 8, we can say that 8 is the same as 4 times 2. Those are its factors. But we can break down the 4 even more. 4 is not a prime number. And in fact, we can say that 4 is 2 times 2. And 2 is considered a prime number, so now we have our prime factors for 8. 2, 2, and 2. And we do the same thing with 12 and 15, and then from there we'll see what the largest collection of each prime factor is. Okay, so let's do this for 12. We have 12, we could say it's 4 times 3. Well, 3 is a prime number, so we're fine there, but 4, we're going to have to break that one. So that gives us a 2 and a 2. So the prime factors for 12 are 2, 2, and 3. We'll do that once more for 15. And 15 is going to be 5 times 3. And we can't go any further because 5 is prime and 3 is prime. So now we have all these prime factors for 8, 12, and 15. Now to create this least common denominator, we're going to look at the largest number of each listed factor within our given values. So at this point, we have 3 prime numbers that we're looking at, 2, 3, and 5. So if we look at 5, we have the largest number of 5s in one setting is in 15, where we have 1, 5. So we're going to use that in creating our least common denominator. And then if we look at 3s, well, 12 has 1 3, 15 has 1 3. 8 doesn't have any 3s at all. So the largest number of 3s we have within a given value set is just 1 3. So I'm going to select just 1 3. I could have selected this 3 or that 3. Doesn't matter. I'm just selecting one, and either one would have worked just fine. Now when I get to the 2s, let's look at what happens there. I have 3 2s for 8, and I have 2 2s for 12. We want to collect the largest collection. We want to select the largest collection of the prime factor given within a particular value. So that means we're going to select the 3 2s from 8. We don't select the 2 2s from 12 because there's another one of our primary values that had more of that prime factor of 2 than the others. Okay, so that means we have 3 2s, 1 3, and 1 5. So we're going to take those numbers and multiply them together. And to make sure we have this written, we took the most number of each prime factor. Okay? So that means we're going to do 2 times 2 times 2, and then times 3, and times 5. Because if we multiply all those together, we should get a number that is a multiple of 15, 12, and 8. So 2 times 2 times 2, we already know that's 8. And then we have 8 times 3 times 5. Well, 3 times 5 we know is 15, so we can say 8 times 15. And if you want to use your calculator, or you can think about a clock and the different positions on a clock, you have this position, this position, this position, and this position. And the idea is that you'd have 15, 30, 45, 60, and then you continue back around again, you come up with 120. So your answer for number 7 is B. Now again, this is one method you could use of finding your prime factors. The other would be to find the least common multiple of 15, 12, and 18. If you did that, you would find that when you look at the multiples of 15, you come across 120, and for 12, you'd also come across 120, and 8, you'd come across 120, and that would be the lowest or the least common multiple for each of these values. Okay, so that takes care of number 7. Next up, we have, this should be, yes, 32. So number 32, we're told that we have television screen sizes that are similar in shape. And Hector has changed from watching a television with a 13-inch screen to a similar 19-inch screen. So if it's saying that if a boxcar, so some image appears 8 inches long on his 13-inch screen, how long to the nearest inch will it appear on the 19-inch screen? Now the fact that these two TVs are similar means that we can use this idea of proportion. And proportion means that we can set up essentially a ratio that relates one object to the other. So we know that our old TV, in the old TV you had a 13-inch screen, and that if you were watching TV on that 13-inch screen, a boxcar, in this case, appeared as 8 inches long. So if we compare that to the new TV, see how this is looking like a ratio or proportion problem? We see that we had our new screen size of 19 inches, and we're trying to figure out how long that boxcar would look in this new setting. So what do you do at this point? You got it, cross multiply. So that means we're going to take the 19 and 8 and multiply those together, and then the 13 times, I guess we should change this to an x, that would be good. So if we change this to an x, there it is. That means that we end up with 13 times x equals 19 times 8, which I'm not mistaken is 152. 152. So now we solve for x. So to do that, we divide both sides by 13, and we get that x equals, I have this in fraction form, 11 and 9/13. So if we take that and we round it, we find that it comes really close, or it's closer to 12 than it is to 11. So that means our answer is G. It's going to be 12 inches long. That boxcar is going to look like a foot long on this new screen. Now, we set this up with old on one side and new on the other. That's one way to do the proportion. Another way we could have done the proportion is to put all of the values related to the old TV in the numerator and all the values related to the new TV in the denominator. That totally works the same way too. I'll just do a quick sketch of it over here so you can see it. So if we had old over new, that means you'd have 13-inch screen, and then you would have that it was 8 inches long, and that means that you'd have your 19-inch screen and you wouldn't know how long the boxcar looks. Look at what happens when you cross multiply this one. There it is all over again. 13x equals 152. So it's the same as what we had over here. You just want to make sure, however you decide to set it up, whether it's old over new or old on the left, new on the right, that you keep your values consistent. You would have just screens in this column. You'd have just boxcars in this column. Or you'd have just screens in the numerator, just boxcars in the denominator. Okay? So that's how you work out problem number 32. Now the next one I've listed is number 40. There we go. So with number 40, we're looking at a gold foil that goes around the outside of an elliptical picture frame. They give us a formula, which is P equals pi over 2 times the square root of 2 times h squared plus w squared. And they tell us that h is the height and w is the width. Now they're saying that the elliptical frame has an outside height equal to 4 inches. So that means that h equals 4, because that's the height, h. And then it has an outside width equal to 3 inches. So that means that our width, or w, equals 3. And they want us to figure out what the perimeter is in inches. Now with this problem, it's just a matter of taking the values that you have and plugging them into the formula that's been given. So we want to make sure that we remember our rules of please excuse my dear Aunt Sally, sometimes known as PEMDAS. So parentheses, exponents, multiplication, division, addition, subtraction. And we go in that order to solve this question. So let's go ahead and set this one up. I'm going to change my pen color here. I'm like in blue right now. Here we are. I'm going to rewrite this formula. I'm just going to copy it straight down. So I have pi over 2 times the square root of 2 times h squared plus w squared. Okay. So they tell us that the h is 4 and the w is 3. So I'm going to take my eraser. I'm going to put, instead of the h and the w, I'm going to put the values of 3 and 4. And then I just solve from here. So again, parentheses first. So that means I need to do this before I multiply it to 2, but you knew that already. So I have pi over 2 times the square root of 2 times 3 squared is 9, 4 squared is 16. So I have that now underneath my radical. We'll keep going. I have pi over 2 still on the outside. Square root of 2 times 9 plus 16 is going to give us 25. So that means I have 2 times 25, which is 50. Okay? So at this point, you have one of two options. One, we can rewrite and simplify the radical. Or two, you can put this into your calculator, figure out what the value is, and compare it to the answer choices that you have here. Okay? So at this point, we can rule out just by looking at it that it shouldn't be j, because you have this plus 3 piece that's added on there. That doesn't make sense. And then we have, again, that plus 3 here that doesn't line up either. So now we have just f, g, and h to choose from. Now, if I put this radical into a more simplified form, that means that I need to figure out how many perfect squares, or what perfect squares are in 50. So for example, if I had the square root of 16, you would tell me, well, that's just 4. And the way we could say we knew that is because 16 is 4 times 4. We multiplied by the same number, and because it's a square root and this was squared, we could just take one of those roots out. So let's try that with 50 and see what we come up with. So 50, we could describe that as 25 times 2, right? And 25, we could say, is 5 times 5. Oh, look, there's a couple. Just like we had 2 4s, we have 2 5s. So that means we can put a 5 on the outside of our radical. And in this case, we need to keep the radical because we still have a value that didn't have a pair. The 2 didn't have anyone to be paired up with, so it stays underneath the radical. So that means when I come back over here on the right, I can rewrite the square root of 50 as being 5 times the square root of 2. 5 times the square root of 2. So at that point, let's do some looking around. I know it's not going to be g, and I know actually that it's not going to be h because notice that I have divided by 2. I can't put these two 2's together, and in fact, it has the square root of 2 still there. So that means my answer choice is F. Okay, so that takes care of number 40. And I think I have just enough time to quickly talk about number 41. Let's see if I can pull it up. There it is. For this one, I'm going to actually put this on the beginning of the next video that I'm doing since I have a limited amount of time. But know that number 41 will be the last of the elementary algebra questions. In this case, we need to figure out what our common factor is, and we'll look at that more so in the next video. All right, see you soon. Bye.